Good morning, everybody. It's 11 o'clock and today is Wednesday, I think. We are gonna do some more science discussions and some fun educational activities. Some of these things are probably stuff you've done before or you've seen or read, but I recommend you try it yourself. And what I'm gonna do is try to give you some terms, some vocabulary terms, and explain some of the processes, the science processes that are behind the things that we are looking at. Before we get into the stuff we're going to talk about today, I want to do the show and tell of what we've done already. So we took an egg. We were talking about semi-permeable membranes yesterday. And so I took a regular raw egg and I put it in a container of vinegar, which hopefully dissolved the shell, which of course we can see that it did. All I did was stick it in the vinegar. It was for about 24 hours. And now I'm just rinsing off the remaining material that's stuck on this membrane. What is left is the semi-permeable membrane that surrounds the inside of the egg. So this is actually very soft. It feels like a very full water balloon. You can see, if you hold it up to the light, you'll be able to see that the yolk is still inside. The egg white is still in there, the albumin of the egg. And so we have this container that is holding material inside the egg. And this membrane is semi-permeable. Remember yesterday I used the example of it being like a colander. It has openings that allow specific materials through, but things that are too big can't get in or out. And so gas exchange can happen. Air molecules, carbon dioxide gas can get out, oxygen can get in, but water cannot get easily through, cannot get out of the shell, but also the larger materials cannot get in and out. And so we can do some fun stuff with this. One of the things I wanted to determine was if more water can go in. Remember we talked about osmosis and diffusion. Osmosis is when water moves across a semi-permeable membrane and it moves from areas of low concentration of solutes, of stuff that's dissolved, to high concentrations of stuff that's dissolved. So you can see this, actually if you measured this egg before we dissolved it, the egg is a little bit larger now than it was before, and that's because there's a little bit of water molecules in our vinegar, and so they were able to move inside the egg once that shell was dissolved, and it made it a little larger because they moved towards that concentration gradient to go to the higher concentration of solutes, stuff that's dissolved. So what we're going to do is we're going to do one more thing. Actually, we may do two, depending on how long we can get it to go. I like to remove the water from this without breaking that membrane, and it's pretty tough. It's actually pretty tough. I dropped it, it would pop, but I wanted to soak it in. One of the best things to use is a thick syrup, like a K-Rose syrup, which is just a corn syrup. And I don't have any corn syrup, but I rummaged through and I found some regular pancake syrup. And so I'm gonna fill this empty container. Coffee mugs work really great for this, with some syrup. Remember, we're trying to do things that we have around the house, so we don't have to go to the store. I want you to be able to use what you have around the house. And so we're going to submerge this in the syrup overnight, and we'll see what happens, okay? So let me do that. If you guys do this at home, make this a science experiment. Hypothesize, what do you think will happen to the egg? And then we'll talk about that tomorrow. So that's the first thing that I wanted to show you. Next, we talked about how water moves into plants through the xylem, which is one of the types of vascular materials or tissues, the tubes of the plant that transfer water and minerals from the roots up to the rest of the plant. And we took this flower, I cut it in half right up the stem, and I put some red food coloring in one cup and blue food coloring in the other. And if you look at the stem on the inside, you're going to be able to see a little bit you can see the phloem tracks. And then it didn't turn out beautifully on this flower. It really works great on carnations, but I want to show you can see more blue on this side of the flower. And so I'm going to take a petal, see if I can pluck it off. You can actually see some blue. Let's see if I can hold it right up there if you can see it. Can you see that blue? You can see a little bit of blue there, right? Okay, and so we can see, we have evidence that the moisture is moving upward and the water is moving up through that xylem. Remember, there's two types of vascular tissue, xylem and phloem. Phloem is the food that the plant makes, and it transfers that food to the rest of the plant through the phloem. Phloem food, that's how you remember. And so that's a fun thing to do. That's a fun activity. I also want to look at a couple more things we've been doing since the first day, where we had some sprouted seeds. We have two different types of seeds, or conditions that our seeds are being sprouted in. This one, these are bean seeds. There's only 3 in a container. And this one, bean seeds, are 15 in a container. And I want you to see a couple things. First, I want you to see the height difference. Obviously, the ones with the 15 seeds are much taller than the ones with only 3 seeds. Every other condition is the same amount of water, same location, same sunlight, and yet we're seeing this drastic difference. One reason is likely to be that these plants are feeling crowded, the ones in the 15 seed container, and so they don't have a lot of access to nutrients in the soil, and therefore the plant is doing what it can to grow quickly to make as much leaf material as possible so it can photosynthesize more to make food, and also to try to get someplace else. If I pull out these plants, we're probably going to see a much larger root ball, amount of roots in here, because they're going to be sending out their roots as far and wide as they can to be able to compete for the nutrients that are in this soil, whereas these guys can take their time. Now, I'm also looking, they're a little bit weird looking. I wonder if this has to do with the way they were planted. There's always different variables. I would have anticipated that these would be a little bit more open and growing more straight, but they're kind of weird shaped. So I'm not quite sure. We may have to do this one again one day. But I also wanted you to notice the direction that these seeds are sprouting. Can you see how they're all kind of bent this way? That's because today, or overnight, I had this plate oriented this way. Every other day I turn it like this, and that's because they're in a window. There's a sunny window right next to me, and they're moving towards the light. And we talked the other day about how seeds have hormones that tell the seed material which way to send the roots and which way to send the shoots, right? The roots go towards the pull of gravity. The shoots go opposite the pull of gravity. That's called gravitropism. Well, this phenomenon you're seeing with this is called phototropism. Photo is a prefix meaning light, and tropism is a movement or direction that a plant will go. And so these plants are using phototropism to move and orient themselves toward the light, because again, light is critical for them to survive. They got to orient those leaves to get as much solar energy as possible so they can photosynthesize. And so I want to talk a little bit more about that, but I want to show you the other group of seeds we have as well. The one where we had 2 seeds, groups of seeds in trays. These seeds are growing exposed to the sunlight, and the other tray is not. It's covered up. But again, you can also see, if you look a little more closely, these seeds have that same phototropism orientation where they're moving this way towards the sun. So I'm going to turn them around overnight again so we don't get really wonky shaped plants. But let me just show you the other ones that have been covered up. Running out of table space. Look at these guys. Oh, these poor seeds are trying their best to get to some sunlight. Look how tall and leggy they are. They are not showing phototropism. In other words, they're not all moving towards the same direction because they don't know where the light is. And so they're going every way they can in an attempt to try to find solar energy so that they're able to survive. So we're going to keep that covered up again. And you can kind of see how interestingly we can observe how plants behave just by taking control of a couple of those different phenomena. Now I want to show you what I meant about the phototropism. I'm going to keep these guys here. Plants have cells that have cell walls. They're very rigid. And then inside a plant cell is a container called a vacuole. The central vacuole, which is the vacuole or the container in the center, I think a vacuole, vacuum, it's like a hollow container. Well, the central vacuole is full of water, and a plant will fill that vacuole with water and as it does, the vacuole pushes against the hard sides of the cell wall to create this pressure. It's called Turgor pressure. Turgor, pressure. Okay, and so when a plant has enough water, that central vacuole fills up and pushes against the sides of the cell wall and creates that stiffness that a plant needs to stay upright. It's kind of like a balloon, and if you imagine that this is a hard cell wall, I'm just using the cup here, and the balloon would be the central vacuole. Let me blow this up a minute. Okay, so if I filled this up, I'm going to fill it up with air, but if the vacuole is filled up with water, you get the same phenomenon. Watch what happens when I fill up the balloon. And you see how it's pushing against the side and holding it. As a matter of fact, this is a fun little trick you can do with people. You can say, I want you to pick up this cup using this balloon without touching the cup with your hand, just with the balloon. And people will try all kinds of things like this, but all you got to do is blow up the balloon and then pick it up and pick up the cup that way. But that demonstrates Turgor pressure, and that's what plants are doing. So if you imagine that there's lots and lots of cells in the stems of these little plants, and each cell has its little water balloon, its central vacuole full of water. And the plant wants to turn this way. What it will do, it will remove some of the water from the balloon on this side of it. It will fill the water from the balloons on this side. So these cells on this side will be stiffer than these cells. So these cells will wilt a little bit. These will be stiffer, and the plant will orient towards the light. That's how come when you don't water plants enough, what do? They wilt, because they don't have enough water in their central vacuoles. Okay, so that's a fascinating way to observe and understand some of the mechanics of how plants move themselves around. These are living organisms, and they do what's necessary in order to survive. Okay, that's our show and tell. We're going to move on because I want to talk a little bit more about water. Yesterday we talked about how water has specific properties, and one of those properties is it has a phenomenon called surface tension. So what I have, I've got 2 pennies, I have a plate, okay, and I've got just a little eyedropper and some water, nothing in the water here. So I want to do a couple of things. I want to show you what surface tension can do. Remember we talked about how it's due to hydrogen bonding, how the hydrogen and oxygen atoms in water molecules, here's my 2 water molecules, and the positive hydrogens and the negative oxygens like to stick together, which makes that stickiness that water gets. And so when you have that hydrogen bonding, it's like they're all holding hands together, and you get this tension called surface tension. And we can see some interesting things that water can do with interesting properties. So I want to start putting drops of water on top of a penny, and we'll count how many drops it can hold. And I'm going to do it up close, so maybe you guys can see a little bit better as I do this, okay? So here we go. 1, 2, and we'll do it until the water falls off. That's 2, 3, 4, 5, 6, 7, 8, 9, 10. Can you see how it's starting to bubble up a bit? That's because of surface tension. 11, 12, 13, 14, 15, 16, 17, it fell. And that's partly because I'm wiggling a little bit. We got 17 drops before it all spilled off, okay? We're gonna try something else. I've got this penny, and this container has some soapy water in it. So I'm just gonna soak it in the soapy water for a second and set it down. Dry my hand a bit. Okay, so this is my soapy penny right here. We're gonna try the same thing and see what happens when it's exposed to soap. 1, 2, 3, 4, 5. It's pouring off already, okay? Because the properties of soap actually breaks the hydrogen bonding a bit and prevents that surface tension from continuing. There's a really fun experiment you can do with your kids. You guys got to try this if you haven't ever done it. You've probably done it before. If you have, maybe you don't know the science behind it. I want to explain. So I've just got a container of water, and I've got pepper. And I'm going to sprinkle the pepper on the water. I think you know what we're doing, right? Okay, so it's floating on top of the water. The water's got that surface tension, right, due to hydrogen bonding. Soap breaks up surface tension. So I've got some soap here. I'm just gonna put a little dot on my finger. Okay, you can't really see it, but watch what happens. Oh, I already broke the surface tension. There it goes. It already got broken. All right, so when you do that, you oftentimes will get that movement of the pepper as it moves with the surface, the skin on the water as the water gets broken. All right, mine didn't work as beautifully, but you guys do that at home and see what's happening. But hopefully now you understand why it's happening. It's because you're breaking the surface tension. Soap is a very interesting chemical because it's actually a long chemical. It's made up of lots and lots of atoms. One side of the chemical easily dissolves in water. The other side easily dissolves in fatty material. You know that water and oil do not mix. That's because oil is made up of fatty material and water is not. And there's different chemical terms for those, but soap is the connector between the two. So when we're washing ourselves, we use soap and water because the soap will connect to those fatty materials, the oils on our skin, and the water part of the water dissolving part of the soap will connect to the water. And so when we wash our hands with water and rinse, it takes the soap molecules and the oil away. That's why just using water won't get rid of the oily materials on our bodies. So that's why soap is such a great thing. Use that soap and water, okay? We understand that much more now, don't we? Okay, well, let's move on. What else are we going to talk about? We're going to talk about gases, okay? I've been talking about materials before, and I talked about how different materials have different properties. We can understand how things behave and the unique behavior of specific molecules and atoms. They're all different in how they behave, and they have unique properties, and so that's how we can identify what they are. And so we talked about how plants use photosynthesis to take energy from the sun, and they produce sugars, glucose sugar, and they produce oxygen. That's good for us because we take in oxygen. But when once we're done with that, our body is done using that, one of the wastes we produce is carbon dioxide gas, which carbon dioxide is something that plants need in order to photosynthesize. It's a great partnership, isn't it? But carbon dioxide has different behaviors as a molecule compared to oxygen, and one of those things is things can't burn in the presence of carbon dioxide. So I'm going to show you, I'm going to make some carbon dioxide really quick. We have got some vinegar right here, and I'm going to add some baking soda to it. If you've ever mixed vinegar and baking soda, you see how it makes some bubbles, right? Those bubbles are carbon dioxide gas. Now, carbon dioxide gas, one of its properties is it has more mass than air molecules, so it floats lower than air molecules. So right now, as the carbon dioxide gas is building up in here, it's pushing air molecules out. And so I'm going to add a little more of this baking soda to make some more carbon dioxide gas. I want to do enough to make it mostly carbon dioxide gas just sitting in this container. Let's do a little bit more vinegar. A little more baking soda. I really want to push all that air. Okay, now we know that fire needs oxygen in order to continue to burn. So when I light this match, it's gonna burn. It'll burn for a while. It'll burn all the way down until it touches my fingers, right? That's because it's got plenty of what it needs. It's got fuel in the match, and it's got oxygen that's taking from the air. But when I put the flame down in the container, watch what happens. Do you see it go out? I'm going to turn it again. Let me just gently turn it. There's nothing but carbon dioxide gas inside this container right now. And so that is, without being able to see it, I know because the flame goes out. Do you see that? It's not touching anything, but it's going from regular air up here to carbon dioxide, and it snuffs out the flame. Okay, so that's how I know that's carbon dioxide. We come in contact with carbon dioxide all the time. I have a container of bubbled water. What is this called? Sparkling water. The reason why we have sodas and sparkling water and other things like that is that they have carbon dioxide dissolved in them. How do I know it's carbon dioxide? Well, of course, I know a little bit about how it's made, but if you don't know, this is not as bubbly as some container or carbonated beverages. That's why they're called carbonated. They've got carbon dioxide in them. But let's just see how much carbon dioxide this has. You see the bubbles coming up? Those bubbles are carbon dioxide gas that's been dissolved in this fluid. And so let's try it again. We'll see if it works the same. And it goes out. Not touching the fluid, it's just going out because this is also containing carbon dioxide. You can actually do another fun experiment where you can make a whole pitcher of carbon dioxide. As long as you don't stir it around too much, you can create a balance using an old broom handle and 2 paper bags. Both of them will be filled with air, but then you take your carbon dioxide gas, which you can't see, and you do this. And it's pouring. I can't see it, but it's pouring right now. It'll pour into one side of your balance, and you'll see your balance tip. Because carbon dioxide, one of the properties is it's more massive. It has more mass than air, and so it will make that balance go this way. It also prevents fire from burning, and so that's another property that we see, which is really kind of a fun thing. Oh, okay, I've stirred it around too much. Now there's air back in there. Okay. Well, that was all we wanted to talk about, but I wanted to end with one more thing, and this is something that I had to run off the grocery store really early this morning, and I saw some Peeps. You know, this is Easter season, and I don't love to eat Peeps, but there's something really fun you can do with Peeps. So if you find yourself having Peeps and you don't want to eat them, come with me. We're going to go do something really fun. So we're going to walk with me into my kitchen here, and I've got some Easter Peeps. I don't know how to turn this around. That's okay. We'll just have to do it this way. This is good. All right. So all you need are some Peeps. We're going to do something called Peep jousting. It's so fun. You should actually play some exciting music in the background when you do it. Peeps are basically marshmallows, okay? And so they are filled with sugar, gelatin, and air, whipped up really heavy, so there's a lot of air in these things. That's why they don't weigh very much. And so air is a gas, just like the stuff we're breathing. When gases get extra heat in them, they expand. They take up more space. They start moving around a lot. They have a lot of energy. When you add heat to gas, it makes those molecules move really fast. They start moving around. So when we heat these guys up, they will start to expand because the gas molecules inside of them, the air molecules inside that marshmallow, will start to bump around. And as it does, it pushes up against the gelatin and the sugar molecules and makes it get bigger. And we're going to do it in the microwave because the microwave heats up those molecules really, really fast. And so it makes them more noticeable how they do it. But what we can do is something called peep jousting. You can take a couple of toothpicks. You can give each of your Peeps its own little lance. So I've got a lance for this guy. Okay. Now this guy's going to have another lance. And you can have Peep wars doing the jousting. Okay, do you see how, look how cute he is. His little, this is so sweet. Yeah, okay. So these guys are going to fight. They're going to do battle. And actually we're going to see which one pops the other one first. Because when the toothpick actually hits the other one, they'll pop. So you can do this. You can determine who's going to fight who. Set it up. I'm getting Peep sugar all over me. Okay, and then we're going to see it. Maybe you can watch this in the microwave. We'll see what happens. Which one will pop. In fact, I'm going to put this little bit of skewer next to this guy so we can tell who is who. So I don't know which one. Take your guesses which one you think is going to hit the other guy first. As they grow, their little lance is going to push against the other guy. I'm going to try to orient them so they're facing each other like this. Okay. So do you think it's going to be toothpick guy or the guy without a toothpick? Let's see. Here we go. It's going to happen fast, so here we go. They're growing. Can you see them get bigger? Oh, they're not close to each other. Nobody's popping. Look how big they get though. Can you see that? Ah. All right, they didn't pop. We're gonna have to do this again. It was a dud match. Look how big these guys are. Okay, actually this guy skewered this guy. You can see it. Oh, look how sad they look now. You can have fun with this at home. You actually can make s'mores out of these things when you're done with it, so you don't even have to waste it. Make it kind of fun, because they're just basically marshmallow and sugar. But this is a fun activity, but the principle behind this is you have gases that you are adding energy to, and when gases heat up, when they get more energy, they move faster and they take up more space. They expand. And so that's the chemical principle behind it, but it's fun to do it in the form of peep jousting. I'm going to put a couple of extra links of some things that have to do with what we have been talking about in the comment section of this video. I'm going to hopefully come back tomorrow. That's my plan, as long as I can, to help just kind of give you guys something to do, give you some ideas. If you think of some ideas, put them in the comments and share them with us. If you take photos, let me see those photos of what you're doing. I'd love to see what you're doing. Any kind of thing to just help help us all have a good time during this time where we're staying at home and we're trying to keep ourselves active and energized without having to go anyplace. So thanks for joining me, and I will see you this time tomorrow at 11 o'clock.